Hi, in the previous video, we talked about naive approach to partition around a given pivot. In this video, we are going to talk about Lomuto partition that works by traversing input array exactly once and requires constant extra space. Let us understand Lomuto partition. How does this work? Let's take a look at this array. We have been given low index and high index. Also, in the previous video, I considered that pivot is given as an input, right? We were taking P as an input. Here, we are going to assume pivot always as last element, right? In this partition. We'll talk about a solution, a modification to this code when pivot is not the last element. But for simplicity, we are going to assume that pivot is always last element. Always last. We are not taking it as an input, right? To simply understand the algorithm. Then we'll later talk about how to handle if P is an input to us, the pivot is an input to us, or index of the pivot is an input to us, and you want to partition around a random element in the array. The idea of this algorithm is to traverse the input array from low to high, L to H minus 1, right? Your array H is always pivot. That's what we have assumed in the beginning, right? Array H is always pivot. So we traverse from left to right till H minus 1 because last element is pivot. We do not have to worry about that for now. We handle that at the end. We put it at the end at its correct position. While we are traversing, we ensure few things. We ensure this, that the element from 0 to I are smaller than pivot. Elements from I plus 1 to j minus 1 are greater than or equal to pivot. So when we are at jth index, we are sure about these things. We maintain this loop invariability that elements from 0 to I are smaller and these elements are greater than or equal to. How do we ensure that? The idea is simple. You traverse the input array from left to right. If you see a smaller element here, right? A smaller element here. What do? You know that I plus 1th element must be greater. We'll talk about corner cases later though, if there are no greater elements. You know that I plus 1th element is greater. What do you do? Simply, you swap this element with this element and you increment the window of smaller elements. Let me repeat what I just said. If you see a smaller element, you swap the I plus 1th element from this and you increment the window, right? You increment the window size. Your I, now number of smaller elements become more than 1. So let me write down that case. So if array j is smaller than pivot, we are going to increment this window. What are we going to do? We are going to make it like this. 0 and one more element is included here, right? So this element is included here, right? And now this is our new I and j is moved here to the next element, right? This is our new, so this is our new I and this is I plus 1 and this is j minus 1. That's how we proceed if it is smaller. If it is greater, we do not need to do anything because we anyways want to put greater or equal elements in the window from I plus 1 to j minus 1. So if it is greater, this window does not change, only this window extends by 1, right? So that's the simple idea of Lomuto partition. If you see smaller elements, simply increment the window of smaller elements by 1 by doing this swapping and proceed. Greater elements, you're anyways maintaining the end of greater elements till the previous element. So you just increment the greater element. Basically, you don't do anything because your j changes, right? So you increment the window of greater elements. Let's demonstrate this with this array example. So we initialize I as L minus 1. Our window of smaller elements has nothing as of now, right? This is where our window of smaller elements is right now. Now what do? We traverse from low to high minus 1. and we check if array j is smaller than pivot or not. So what happens here? J is right now here. This array j is smaller than pivot, right? This is our pivot also. So pivot is 70, we've written it here, right? So it's smaller than pivot. So what do? We go inside this if condition, we increment I. We increment the window of smaller elements. I becomes 1, right? And we swap array I with array j. Where is j right now? J is here. Let us do a dry run of this algorithm for this example. We initialize I as -1, L -1, right? So L is 0, so our I is -1. So our initial I is here because we do not know how many smaller elements are here in this array. So we just keep it before the first element. Now we run this loop. And what do? We begin from j equal to L. So our j is 0. J is here right now. And we compare it with pivot. Pivot is 70. So it's smaller than 70. So they go inside this if condition. And what happens when they go inside this condition? They increment I. We increment I and we swap the elements. We increment the window of smaller elements. So I now becomes 0, right? And j is anyway 0. So 10 is actually swapped with itself, right? So when you were here, your initially I was -1 and here j is 0. So I is incremented, I becomes 0 and j remains 0. So the element is swapped with itself. Although you're doing swapping with itself, but your window of smaller or equal elements is increased. So this is now your window of smaller or equal elements. It has one element only because I has now become 0. And j is moved to next position after swapping. So when now j comes here, right? When j comes here, you again compare 80 with the pivot element. Pivot is 70. So when array j is greater, you do not do anything, right? You do something only when this is smaller, right? In greater or equal cases, you do not do anything. So you keep 80 as it is and you move to the next element. So you come to j equal to 2 here, which means 30. So you are currently at 30. You compare 30 with 70. So what happens when you compare 30 and 70? 30 is actually smaller. And what do we do in smaller case? We increment the window of smaller elements. So I now becomes 1 and we swap these two. So 30 and 80 are swapped. So you have 10, 30, 80. So these two elements are swapped by this statement. You increment the window of smaller elements and then you do swapping. And your I becomes 1 now. So your window of smaller elements is this. And your j becomes 3. So your j reaches here. This is window of greater or equal elements. This is window of smaller elements, right? So what will happen when your j is 3? You will see that 40 is smaller than pivot, right? So what you'll do? You will again do swapping. So you will increment the window of smaller elements and you will swap 80 with 40, right? You will do I++ and you will swap 80 and 40. You increment the window of smaller elements and then you do swapping. So your I becomes 1 now. So I is now 1 and j is moved to the next element 3. So we were here at j equal to 2. Now we moved j equal to 3. So our window of smaller elements is 0 and 1, right? This 10 and 30. Window of smaller elements is 10 and 30 here. Here also we have 10 and 30. So j is 3 now and j3 means you are here at 90, right? And what happens when we see a greater element, greater or equal to element, we simply ignore it, right? We do not do anything, simply increment the j. So this is now your new window of greater elements, right? New window of greater elements, simply ignored it. And this is a window of smaller elements. Then you move to next element, j becomes 4 now. So what do you do when j is 4? It's smaller than pivot, right? So 40 is smaller than 70. So what do? You increment the window of smaller elements and then you do swapping. So the window of smaller elements now become 10, 30 and 40 because you have swapped 40 and 80. You increment I, right? And then you do swapping, right? So your I becomes 2 now and your j becomes 5 now, right? You have 3 elements in the smaller window, right? And now you move to the next element, which is 50. I is 5, 50. So what happens? This is again smaller. This is again smaller. And what do? You do increment the window of smaller elements and then you do swapping. So the window of smaller elements is increased. It becomes 3 now. And you have swapped 50 and 90, right? These two are swapped, right? So 50 comes here and 90 goes here. And this is your new window of smaller elements. And this is your new window of greater elements. After this step, J becomes 6. And your high is also 6. We run a loop from L to high minus 1. So we stop here because it has gone beyond high minus 1. So we stop the loop here. And you can see that all these elements are smaller and all these elements are greater. And your pivot is here. So what do you do at the end? You swap your pivot with the first greater element, right? So you swap 70 and 80. How do you find the first greater element? Using I plus 1. Your I is 3. So when you do I plus 1, you will come here, right? So you swap these two elements at the end. I plus 1 and H. H is your pivot, right? So after swapping, what will you get? You will get 10, 30, 40, 50. You have swapped I plus 1th element with the last element with your pivot. So you will get 70 here and 90 here and then 80 here. So you have pivot at its correct position. You have all the smaller elements on left side, all the greater elements on the right side. So if you want to return the index of pivot, if you want to return where your pivot is after modification, you can return it again as I plus 1. Because this is where pivot is, right? You swapped pivot with the I plus 1th element. And you're sure that I plus 1th element is going to be greater. Because your window of smaller elements is from 0 to I. And window of greater elements is from I plus 1 to last element. To get a better understanding of Lomuto partition, I strongly recommend that you try these corner cases yourself. I'll give you an idea what happens in the corner cases. So this is a corner case because the pivot element, the last element that we always consider as a pivot here in the algorithm, the pivot element is smaller than all the other elements, right? So do a try run and see how will your algorithm work, because there is not going to be any window of smaller elements. So what will happen in this case? Your I is initialized as -1 here, if you are considering L as 0, right? And then you will continue doing J++, 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 and you will stop here. I will never change from -1. So the window of greater element is all the elements, right? And window of smaller elements is empty. What do you do at the end? You swap array I plus 1 with the pivot. So what will you do? You will swap 70 and 30. You got the answer right. 30, 60, 80, 40, and then you will get 70. So you have your pivot at correct position and you have all the greater elements on right of it. And you can find the position of pivot also, right? Using I plus 1 again, right? Using I plus 1, we can get where pivot is. So it works for cases when your pivot element is smallest of all. Let's now talk about what happens when your pivot is greatest of all. Please do a dry run for this particular case also. Let us see what happens. We initialize I as -1. So when we are here, our J is here. We see that array J is smaller than pivot. So we'll do I plus plus, right? And we'll swap array I and J. So we are going to make the window of smaller elements of size 1. I becomes 0 and we are going to swap array I with array J. So J, this element is going to be swapped to itself, right? That's what will happen. Then you will come here. You will increment the window of smaller elements and you will swap array I with array J. So which means the 40 is going to be swapped with itself again. So the window of smaller elements is going to become this. And you will swap 40 with 40. Now what will happen? You will come here and it's again smaller. So you will increment the window of smaller elements further. And you will swap 20 with 20. Your I will become 2. What will happen when you come here? you will increment the window of smaller elements and you will swap array I with array j. So 50 will come here and your array I will become 3. Right? So your I at the end is 3. Right? This is your window of smaller elements. And at the end, what do? You swap array I plus 1 with pivot. What is array I plus 1? This 80. So you will swap the element, the pivot element with itself. So you have your original array as it is. You just did swap of every element with itself in every iteration. And at the end also, you did the same thing. And you can see that your position of pivot is I plus 1. It's 4. So this way, you could partition even the array which is all the elements smaller than the given element. So far in Lomuto partition, we have been assuming that pivot is always the last element. What if I give you an element which is not the last element and I ask you to partition the array around this element? What if your P is an input parameter, index of the pivot element is an input, right? I tell you that partition the array around this element. I tell you the index of P pivot element is 2. What changes you will make to Lomuto partition to handle this? This can be done simply. See, the standard Lomuto partition assumes that pivot is always the last element. You can simply do a swap between this and the pivot, right? So you just need to add this line, swap array P with array H. What will happen after this? Your array will change to 50, 30, 11, 10, 5 and 20. So your 20 moves to the end. Now you can run the standard Lomuto algorithm on this array, right? Your pivot is at the end. You wanted to partition around 20, you will get the partition around 20. In this video, we talked about Lomuto partition. Lomuto partition partitions an array around a pivot in big O of n time. It requires big O of 1 extra space. Also, it does only one traversal of the input array, right? Unlike naive partition, which was doing 3 traversals. So obviously, it is better than the naive partition. There is one more partition algorithm called Hoover's partition algorithm. On average, Hoover's partition algorithm works much better than Lomuto partition.